Okay, so at this point, we have discussed quite a bit. I mean, gosh, is he ever going to stop? Are these videos actually going to stop coming my way? I need to get caught up. Oh, we're almost finished. I promise we're almost finished. There's just a couple of left. But the reason that I'm kind of saying this right now is because all of these issues have created something that we need to be a little bit more concerned with. So we've talked about water and we said high temperature, high pressure. We talked about steam and we said high temperature, high pressure. We talked about clean in place and sterilization in place and sterilization, high temperature, high pressure. So as you can imagine, the problem here is that we are generating a lot of heat and we're generating a lot of pressure in a normal working type of situation. So we have to kind of talk about the other things that are going to come along with these utilities, because that's what these things are. Remember, module title. So cooling systems and heating systems are going to be a thing in the biomanufacturing arena. So as you can kind of imagine, again, use common sense here. Cooling systems will cool things and heating systems will heat things. Oh, what? No way. Are you kidding? No, I'm not. It's as simple as that, folks. I promise. So as far as the cooling systems go, well, they can use water, absolutely, or they can use some type of coolant. Coolant is the magic word. And I want you to think of maybe like your car. Okay, so up underneath your hood, you've got a cooling system. You've got something that circulates throughout, up underneath the hood, through all of the popping, through all of the valves, through all of the pumps. Oh, wait a minute. I thought you were talking about vehicles. I didn't think you were talking about biomanufacturing. Oh, well, it's kind of the same idea, the same concept, right? So this coolant is going to be used and it's going to circulate throughout the biomanufacturing plant, and that coolant will cool super hot stuff. Okay, well, that's great, but there's more to it than that. And then heating systems are going to be heating the stuff, and most of the time, steam is actually going to be the most common heat source here. So this is why we talked a little bit about water, we talked a little bit about steam, we talked a little bit about the purposes of those types of things, and here it's coming back again because now we can reference these to the cooling and the heating systems that's going to be within the plants, most of the time within the plants, doing another specific type of purpose for us. So all of the cooling systems and all of the heating systems can be found throughout the manufacturing process. Again, it really depends on what's getting made. That's where you're going to find some of them. But you will often see things like jacketed tanks. So we talked about tanks and fermenters and blah, 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 blah. And we said that there are cooling mechanisms or heating mechanisms in place that we can control the temperatures of those things. Heat exchangers, well, if you exchange one thing for another, you're swapping it out. So that means that heat is getting swapped out in a heat exchanger. Okay, well, we'll talk a little bit more about that in just a minute. We can also see things like chillers, which means keeps things cold, liquid nitrogen, of course, cooling towers. All of these things are part of the biomanufacturing process, and that's the intention of them. The intention is to heat and to cool things and to be able to control it in a very safe environment. Okay, so heating and cooling, if we want to go a little bit further, well, jackets, back in the day of many hours of lecture videos ago, we talked about jackets, and we said that jackets were like walls around these tanks. So think of the tunnel inside of a tunnel, right? I probably mentioned like a straw inside of a toilet paper roll. Well, okay, on the outside of that straw, within the toilet paper roll, there's going to be a void, and that void could be filled with some type of fluid that can heat up or that can cool down. So it keeps that tank, whatever tank that might be, it keeps that tank warm and toasty, or it keeps that tank super, super cold, so that way it can do what it was designed to do. This could be water. Absolutely, water is a coolant. There is no questions there. But water might not cut it, because water, it might need to go a little bit colder than that. And depending on the nature of what we're trying to do, chemicals can actually be used. And those chemicals can be ethylene glycol or something similar. So ethylene glycol is very similar to your modern day antifreeze, and ethylene glycol can be used. Don't ask me. I have no clue what just happened to my computer screen. So let's just keep on going, right? I don't think there's anything like my personal social security number for you to steal and take. Identity thefter. Well, I don't think so. It was probably just a couple of boring screens that you saw a while ago. Anyway, coolants can also be things like ethylene glycol. And this is very similar to antifreeze that you would put into your vehicle. And the reason is because that your engine coolant, and it's making sure that your engine doesn't overheat. So it's a fluid that circulates. It can grab heat. It can take away heat from another type of material, and then it just recirculates and goes through the same exact process over and over and over. Absolutely wonderful. Absolutely great. Same kind of stuff can be used in the biomanufacturing plant as well. Heating fluids, just like coolants, water can be an acceptable heating fluid, but you can also see steam and some organic fluids. Organic fluids can sometimes heat up a little bit hotter, retain heat longer, whatever the case might be. One is called Dowtherm. It's like a manufacturer specific name, a brand name in a way, of an organic type of material that can go into these systems and be a heat fluid that we can use in the biomanufacturing process. So as far as the heat exchangers, the chillers, the liquid nitrogen, the cooling towers that we mentioned on the previous slide, here's a little bit more detail about each one of them. Liquid nitrogen, which is kind of what I want to mention at this point, that is very good to go super, super cold. And take a look at this temperature, negative 70 degrees. Oh, God. Don't put me into that chiller, please, because I definitely do not want to go negative 70 degrees. But these are great for cell cultures. And very often, sometimes these things have to stay frozen. And that way we can preserve them or do whatever we need to do with them. So ultra low freezers are going to be a common thing in a laboratory setting. And sometimes these chillers that are using liquid nitrogen can go super low to negative 70 or even lower than that if needed to preserve these types of biologicals that we are using on a daily basis maybe. Cooling towers, just as before, if they're not heating towers, they heat. Cooling towers remove the heat. So cooling towers are going to take something extremely hot and they're just going to cool it down safely so that way they are not as hot any longer. So again, I hope that these types of things make sense. As far as heat exchangers go, well, okay, let's kind of look at some diagrams here. I get some hot water in. Okay, here we go. So now it's going to go down the pipe and out the other end. So hot tamale. I mean, that's what this thing is, right? Okay, so this is going to carry some heat. It's a very hot liquid. How can we cool this very hot liquid down? Well, if we've got some maybe airflow or we've got some super chilled water, like, hey, whoa, you want to go to the, okay, not that kind of chill, but if we've got some cooled water or cooled air or something that is cold and we rush it across this piping that this hot liquid is kept inside of, that it's flowing through, then that really cold airflow or that coolant or that water is able to chill that piping down maybe and the material on the inside of that piping, and therefore hot water goes in but cooled water ends up coming out. So again, I hope that kind of makes sense. I think that you would do this at your house. So if you've got something super, super hot, maybe out of the stovetop or out of the oven, and it's in some type of container or some kind of jar, and you're like, oh gosh, I'm going to have to cool this down quickly. What you would do is you would go over to the sink and you would turn your faucet on and you would allow that cold water to hit the outside surface of that jar, and it would cool the contents down on the inside a little bit faster. So that's kind of what we're doing here. It's just mass quantity scale. Well, there's two different versions. You know, look at this one up here at the top, hot water in. So if we want it to stay in contact with that coolant a little bit longer, then we lengthen the tube that it's going to be contained within when it's exposed to that coolant or to that cold air or to that cold water. So you get the picture, right? So the longer it stays in that tubing, the more chances of us cooling it down and getting it a little bit colder. So there's different kind of versions of these coolant systems that can go on, or these heat exchangers really, that can go on here. And it really just depends on the nature of what we have to do, right? So if you look at some of these diagrams, this is what you're going to see over on the right hand side. This says main process flow in and main process flow out. That is your material. That is kind of the stuff that needs to be cooled down because it's super hot maybe at this time. So this is me in my car and I'm going, so that stuff needs to be cooled down. And the way that they like to depict this is some type of circle, right? And then they put this little jiggity jag line in the middle of it, and that is their representation of a heat exchanger. So what happens is that some type of coolant, if we're trying to cool this stuff down, or some type of steam, or some type of heating fluid, if we're trying to heat it up, will go into the system and it will do what it is supposed to do. It will heat up that fluid or it will cool down that fluid, but that is the way that these look in these type of diagrams or schematics that you will see. So that is the representation of a heat exchanger out there in a schematic type of world. So now we can read those maybe a little bit better. I know I've got stuff coming in and out, but then at the same time, coolant or some type of heated fluid has to go in and out as well. As far as technicians go, what is my responsibility? What should I be looking for? Well, number one, of course, it is temperature driven. So you need to make sure that you monitor the fluid temperatures. So are things staying as cold or as hot as they need to as far as the fluid goes? And take a look at the temperatures of the process flow. So the stuff that's coming in and the stuff that's leaving, is it really getting cooled down or is it really getting heated up? So temperatures are going to be a very important piece to that puzzle and give you the answers that you're looking for. Number two, monitor that transfer fluid. So that's kind of what I just said, right? The transfer fluid, all of these coolants, all of these heating elements, everything that goes on in that exchanger system, the heating or the cooling towers, whatever the case might be, you're looking at temperatures of everything. Temperatures also are related to pressures. So sometimes pressure gauges are going to be on these things. We constantly want to look at them. We want to monitor them. We want to log them, make sure they're not getting out of specification. Number three, if I'm working with cooling, I want to avoid frostbites. Those are as bad as burns because they do somewhat burn your skin if you're not really careful with them. So go back and think of the Christmas Story, and they're out there looking and making fun and, you know, oh my God, stick your tongue on the light pole and get it stuck. And how do we get it off? Oh, okay. Well, frostbite and cold weather is as bad as hot weather or hot temperatures, and here is a case or that type of scenario. So if I'm going to avoid frostbites, I'm also going to avoid burns, and if I avoid burns and frostbites, especially I'm working around liquid nitrogen, I want to take special care. That fluid is super, super cold, negative Celsius, right? Keep that in mind. -70 or colder, of course. So that liquid nitrogen is going to be a powerhouse when some of the cold or some of the frostbiting or some of the contact damage is going to be experienced. So just be careful with it if you do use it or if you do work around it. This is also going to lead us into something called hydraulics. Hydraulics is the whole piece that we talked about a little bit with gases, right? We have an intake, and that intake is going to be a gas, and that gas is going to apply a pressure maybe on something, and that is going to move that piece up and down. So all of these pneumatic types of pieces we were talking about back in the day when we were looking at valves, and this was an idea that gases allowed us to apply pressure onto something in order to control flow rates. Well, okay, now that we're talking about liquids and now that we're kind of dancing in this realm a little bit more, we can also bring up the concept of hydraulics, and this is the same type of situation. Except for it's not really gases here, it's really liquids that are used. So liquids are pumped into some type of system with a moving device, and that pressure based on the liquids that we are pumping in or sucking out will be able to do things, work or flows or whatever the case might be, however that hydraulic is made. That's what we are really referring to here. So the good thing about them, they do have greater forces than gases, and that means I can increase the pressures here a little bit more or a little bit higher than what I can with gases, and that might be a good thing, it might be a bad thing, but this is the option out there for hydraulics. So I just kind of wanted to briefly mention it, just saying, hey, this thing is a possibility. And because we're talking about coolants and because we're talking about fluids and because we're talking about these types of liquids doing things for us, well, hydraulics is another one of those situations where something can be at play with the help of a liquid, and it can do a job for us. So as far as technicians go, what are my responsibilities with hydraulics? Well, number one, observe leaks, right? You want to make sure it's fluid, so you want to make sure nothing is leaking around these connectors and these fittings. Two, just like before, like always, measure a gauge, measure a pressure, inspect the valves that the fluid is using in order to go in and out of that you can cut on and off, and then avoid crushing hazards. These things can be quite large, and they do operate with extremely high pressures. So the last thing that you want to do is be in the presence of one of these moving pieces and parts, because it's not going to stop for you, and you're not going to be able to put your hands on it in order to stop the hydraulic from happening. So it's probably going to crush you in the meantime. So just be really careful if you do work around hydraulics. Those are some of the safety concerns that we've got to keep in mind as we're out there working on the plant. All right, so next up, we are going to talk about in the next video electricity, and then that will finish up our utility lecture, I believe, and then it will be some waste. So how do we get rid of waste at the end of these processes? And, what are some of the common things that we've got to watch out for when we generate that type of material? So it looks like I've got, honestly, one or maybe two, if even that, videos that are left. So you're almost done. You're almost at the finish line. You're almost ready to take those practice quizzes and that module test. You will do wonderful on it. I promise. As long as you watch the videos and take notes and pay attention, you'll get it.